Nanopores are hollow nanoscale barrels that traverse a biological or synthetic membrane, which allow for free or selective diffusion of various solutes. Applications of nanopores include chemical and biosensing, as well as targeted drug delivery. Peptide nanopores are extremely interesting due to their small size, fast binding kinetics, and ease of synthesis. However, most peptide-based nanopore formers bind to membranes through purely hydrophobic interactions and cannot be made selective for pathogenic membranes, thus limiting their application in targeted drug delivery. Daptomycin is a clinical antibiotic that kills bacteria through binding to their membranes and forming an oligomeric nanopore. This nanopore is really fascinating because it only forms on membranes containing phosphatidyl glycerol, which is a bacterial membrane lipid. Daptomycin also requires calcium to bind to bacterial membranes. The fact that daptomycin forms nanopores only on membranes containing a certain lipid is a unique and interesting phenomenon that could be exploited for targeted drug delivery. Thus, I have been studying the interaction between daptomycin and phosphatidylglycerol in great detail as part of my thesis. Phosphatidylglycerol is unique among phospholipids since it is one of the few that possesses two stereocenters, labeled 1 and 2 in this figure. Since stereocenter 2 has been shown to vary in bacteria, we are currently exploring how stereochemistry at this position affects daptomycin's ability to bind to and oligomerize on bacterial membranes. To elucidate this effect, we synthesized each of the 4 stereoisomers of Pg. These lipids were then used to prepare large unilamellar vesicles or LUVs containing stereochemically pure Pg. DAP's affinity to each of these membranes was measured by monitoring the fluorescence of kynurenine as a function of calcium concentration. When this fluorophore enters the hydrophobic membrane, a large increase in fluorescence intensity and a blue shift in emission wavelength is observed. This property of kynurenine can be used to measure membrane affinity. Monitoring the fluorescence emission at various calcium concentration yields a titration curve with an endpoint that is proportional to the delta G of the membrane binding and octamer formation process. From this experiment, we can clearly see that DAP's membrane affinity is strongly affected by Pg stereochemistry. Interestingly, these data show that DAP actually recognizes the head group of Pg since its binding and oligomerization are greatly affected by the stereochemistry at this position. Placing the same model membranes and DAP in a circular dichroism spectrometer at a calcium concentration of 5 millimolar, we can see that the stereochemistry at the head group also influences the structure of the octameric pore. This is the first time anyone has ever shown that the stereochemistry of a lipid could have a substantial effect on the structure of a peptide-based pore former, and we are excited to explore this phenomenon in more detail with the continued support of the Waterloo Institute for Nanotechnology.